Okay, and good afternoon, everybody. Welcome to the Splash session. Glad that you're here. There was no other place to go on the workshop anyway. The Splash session is basically speed dating for CFDers. The rules are simple. Each of the participants has 3 minutes time. Because it's Friday, we get 3 minutes 30. He can talk about any topic about OpenFOAM. There are no questions. Please feel free to contact the speakers afterwards through the website. With that introduction, I think I will go to the first speaker. I will just have to set up the slides for him. Sorry, okay. Okay, please start.
Hello, everyone. This is Stan Posey from NVIDIA, and thank you for this opportunity. Of course, this work is a collaboration that I'll show you. Next slide, please. Next slide, please. And it started with NVIDIA's participation in the OpenFOAM HPC Technical Committee as part of the OpenCFD branch. We currently have a solution that conforms to the version 2012 that's available in release. And the HPC TC had developed a library, previous slide, please, called PETSI for Foam.
Previous slide, yep.
And that was, a library that provided FLAC 2, please.
Sorry, next slide or?
And what NVIDIA has done is plugged in an AMJX library solution, correct? Back, please.
Yes.
Thank you. And,
sorry.
And by plugging in this library, we've been able to get some really nice results that not only show speedups on the GPU, but allow us to provide OpenFOAM in a way that could be supported in the future by the OpenCFD branch. And this will be available to the Foundation branch later if there's interest. And there's references at the bottom of this page that you can read about the developments that preceded this work that allowed us to develop this plugin solver. Next, please. Here's an example of some speedups. It's a very simple case. It's there's no turbulence, it's laminar. It's a small case of 8 million cells, but it gives you a nice idea of some speedups that are possible. This simple case could be used for replication if you wanted to test our solution. But you can see over a full node Broadwell, and the schematic on the right gives you what these look like. We ran OpenFOAM on the CPU and got a result that we use as one, and then ran on a single GPU that uses a single core of the Broadwell and got a 9.2x speed up with this solution. Next, please. And here you can see a few strong scaling, weak scaling plots, and these are up to 8 GPUs. Again, the same case, the 3D moving lid, simple configuration. Next, please. And we've done some work on ARM. NVIDIA has announced support for ARM. We'll be developing our own ARM CPU to be combined with the next generation GPU. So please look out for that. And here's the result versus AMD, where the ARM is faster both for CPU only and then CPU plus the A100 GPU, the current GPU available. Next, please. And I'll be happy to answer any questions. These slides are going to be made available. I went through very quickly, but there's lots of references there, and we'll be happy to share more about the details of our solution upon request. Thank you. Thank you for the opportunity.
Thank you very much, and thank you. Sorry for the messing up the.
Not a problem. Very good. My first time.
Okay. So the next speaker is going to be Joseph Nudge. He will speak about something not so open source. Okay.
Thank you, Bernhard. Yeah, so I'm going to talk about OpenFOAM in VSL, which is the Windows subsystem for Linux. So how you can run OpenFOAM in Windows 10, more or less natively. So next slide, please. So at the a workshop in Exeter, I believe that was the first Splash talk. There I talked about the Windows subsystem for Linux and how you can utilize it to run OpenFOAM in Windows 10. I remember that back then a couple of people were laughing, at least internally, about OpenFOAM in Windows 10. And so the basics of Windows of VSL is that you can run any Linux distributions in this virtual machine kind of thing, and you can run them alongside Windows desktop applications. And you can access both your Linux as well as your Windows file system at the same time, so you don't need a dual boot. And in my opinion, currently in its state to how to use best Windows subsystem for Linux for OpenFOAM is that you can run pre-processing in VSL, because running block mesh and even for medium cases, Snappy Hex mesh is not much slower than in Linux. And then of course, you copy your files to a Linux server or workstation, where then you run on multiple cores, and then you can copy back and do the post-processing directly in Windows 10 and then paste your results into your PowerPoint. Of course, you can do it in Ubuntu, but if you prefer Windows, then there is this possibility. Next slide, please. And you may be familiar with my YouTube channel. There on the community tab, I did some polls regarding the Windows subsystem for Linux. So I asked people how do they use OpenFOAM, and as you can see, 42% use OpenFOAM in Windows 10 with the Windows subsystem for Linux, and 49% use Linux natively. They use either the pre-compiled version or they compile it on their own, and only 9% of the people use the rest of the options. So Windows is now the second and close to the Linux users. And I also asked how long have the people been using the Windows subsystem for Linux, and as it seems, most people just discovered it in 2020, although it has been around since 2016, but it's starting to gain popularity. So next slide, please. And a very exciting news that soon Microsoft is going to release VSLG with the possibility to run even graphical programs, Linux native programs. So for example, you could use the native ParaView version and run it under VSL, and you don't have to use the Windows version, but that's up to you. So this is some exciting development, and I wanted to throw this out because it surprised me that 42% of at least on my YouTube channel, people do use OpenFOAM in Windows 10, and only 49% use Linux. So I just wanted to throw this out there, and thank you for listening.
So thank you very much. That was valuable information for a lot of people. Not me, but yeah. So sorry, I don't have a Windows machine. No. Okay, the next speaker is going to be Mustafa. Okay, sorry, I don't pronounce it. Please start.
Good attempt, Bernard. Thank you so much. My name is Mustafa Butwawala. Next slide, please. I work with ANSYS Fluent by day, but then I tinker around with OpenFOAM by night. And this is one of those good things that has come about that tinkering. A little relevant comic. A lot of us have the learning curve right at the start, and it's a very difficult process, especially for those of us learning. Next slide, please. Right. What a lot of us do is we probably build OpenFOAM in debug mode. We integrate it with GDB, and then I have a great article on this, which I can link you to after the session. But this is not enough a lot of the times because you have a very narrow code path to explore. You can always set up a language server and then click find all references, for example. So what we have is SourceTrail, which is an open source code visualizer. So it indexes the source code to find all definitions and references within your source code. And as CFD community, we need visualizations. We work very well with them. So this gives us like a big picture of the dependencies that are involved. Next slide, please. And next slide as well. Right, thank you. So we have, for example, a sample code. We have a constructor, a destructor, and a lot of other member functions which are defined in this file. Can you go to the next slide, please? Right, next slide as well. So for example, a simple illustration of what this would look like in SourceTrail is there would be different class members with their access specifiers in a diagram form, which has what it includes with a bidirectional arrow graph. So everything that you need to visualize in sort of a UML format is there for you. Next slide, please. Right, I'm just going to tell you quickly how to do this. You need to tell SourceTrail what source and header files to include, and this might be very difficult to do manually. Luckily, Clang, which is the compiler that can use IntelliSense here, would require some file called a compile commands.json. All you have to do is kind of extract this file. Next slide, please. Okay, so for projects that require, let's say, somewhat of a CMake kind of project, you can use CMake export this command on the screen in front of you. If you use Visual Studio for your other projects, you can have a SourceTrail extension that will generate this file from VS Solution. But for non-CMake, non-VS projects, you have a command called bear in Linux, which will generate the JSON file for you right away. What it does, it runs the build command and it intercepts the instructions, and then it just gives you a nice JSON file at the end of it. Next slide, please. All you have to do is create a source group from this compilation database, which is the compilation commands.json that you created. Then VS, and it's not the only good thing, because VS Code has an extension called SourceTrail, which will let you interactively connect your IDE, in this case, your code editor, with whatever whatever part of the SourceTrail application that you want to link it with. Next slide, please. Right, I can show you this here, for example. So you see a nice little SourceTrail send location at the end. So in your source code, you can directly navigate to wherever in SourceTrail you want to be, and that's really helpful. And as Joseph said, I'm one of those 42% that uses WSL. So you probably have to install SourceTrail and WSL as well, and you have a nice little X server set up. And if you have WSLG, you don't have to worry about that either. So you can combine all this, and you have a very good setup for code visualization in OpenFOAM. Thank you.
Thank you very much. So the next talk. Sorry. Okay, the next talk is by Chandan Bose. And yeah, please start.
Hello, everyone. Yeah, I call myself Chandan Bose, and that's okay. Yeah, so basically, let's have a quick detour to some nice visualization and the physics from the technicalities of OpenFOAM. So I will just give you a very quick glimpse of what I am trying to mimic to test the overset grid strategy that is available in the OpenFOAM framework. And I have actually chosen a very interesting problem of water exit and entry dynamics, which is, needless to say, having many interesting applications. And this work is done with one of my fantastic master students, Vignesh. Next slide, please. So here I will, without going to the details of numerical nitty-gritties, I will just give you some very quick claims that I'm using over Interdim Foam, and basically to test the overset meshing strategy. And for that, to test my validation case, I have chosen some experiment of falling sphere into the steel fluid. And this particular case has 1 degree of freedom in the vertical direction. And although the solver is capable of handling 6 degrees of freedom. Okay, so here the most important thing to mention is the grid priority by the zone ID, by specifying the zone ID to facilitate the cell volume weighting interpolation. Yeah, next slide, please. Next slide, please.
Yeah, is this?
Yeah, so here I basically show you a quick validation with the experiments. Sorry, previous.
Yeah.
Yeah, so you can see that our present calculations, it gives grid converged, and quantitatively it has a very quick, a very nice match with the experiments. And quickly, you can also see that qualitatively we got a very nice match, although not very perfect. We are working on it. And the thing that I want to highlight here is that the post-processing, that we had a nice training in this workshop. I used 2 different post-processing techniques. One is the Blender post-processing, another is the ParaView ray tracing technique. And you can see that even the ParaView ray tracing technique, which is very easy, and as compared to Blender, as we need separate scripts for that, it works very well, and the experimental figures looks fantastic. Next slide, please. Yes, so to test it further, we have taken this case of tandem cubes. Next slide, please. And I can assure you the simulations are grid converged and well validated. And these are some nice contours of the alpha water values. And here we are trying to track the interface and what kind of splashing dynamics it undergoes. Next slide, please. Yes, so this is the volume contours, which shows very nice visualization for understanding the physics. Next slide. Next slide.
Yeah. Okay.
And this is some velocity profiles to give you more physics. Yeah, so in the last 10 seconds, next slide. Last 10 seconds, I want to tell that this was a toy case that we started, but ultimately what next we are moving, I'm interested in the biopropulsion, understanding this fascinating physics of this biopropulsion systems. Thank you. And this is kind of Bernard, I mean, he is showing the video of it. So this is the visualization that I got from ParaView ray tracking, which looks quite nice and comparable to the experiments. And so I would suggest you can try it out. Thank you. Thank you for listening.
Thank you very much. And the next speaker is talking about CO2 capturing from what I get. Sorry, I'm confusing myself.
That's okay. That's fine. Thank you,
Yeah.
Bernard. Can I start? Yeah.
Yeah.
So
Yeah.
hello, everyone. Thank you for providing opportunity. I'm Ashish Kotwal, and I'm discussing here about CFD modeling by using OpenFOAM software for CO2 capture process with the liquid solvents in a post-combustion process in a fossil fuel power plant. Next slide, please. So this is how the post-combustion CO2 capture process, the system looks like in a reality. After coal or oil or gas is burned, the gases contains almost 30% volume basis CO2, and that is getting absorbed in an absorber tower under concept of gas-liquid countercurrent fluid flow phenomena, which was critical scope of this project. Next slide, please. Thus, for a gas-liquid countercurrent flow, fluid flow phenomena, these are the equations considered, and that's why henceforth Interform solver is used with the VOF model. Two additional scalar equations implemented in an OpenFOAM.c file for estimating mass transfer coefficient in conjugation with the Higby penetration model theory. Next slide, please. So this is what the geometrical domain looks like in my simulation. It is based upon a structured Melopack packing developed by Sulzer. Many experimental data is available for this packing. That's why it's been considered. Next slide. There are these are the transport properties of liquid, flow rates for the liquids, and the fluid contact angles are considered. Next slide. And this is what the results looks like. A weighting of packing, structure, geometry. So the first two slides, first three images are basically showing that the weighting of packing structured geometrical domain. And then the graphs are basically showing that the validation of a current applied OpenFOAM framework with the previously published experimental data and simulation results, especially the right lower graph validates the current OpenFOAM based framework in a cohort with the results of ANSYS Fluent based simulations. So this is basically like a code to code comparison that I have done in my project. So next slide, please. So moving on to the conclusion, therefore, so these are the drawn and agreed upon conclusions with the DOE, Department of Energy people, NETL people in this project. So basically the previously published Fluent-based HPC-based simulations and a current quad-core PC-based OpenFOAM simulations show marginalized error of 3 to 7%. If I decide to consider this error, it is acceptable, and because of that, I can actually run the simulation simulations on a regular basis, on a regular PC, and I don't have to go like a multi-million cells, and I don't have to like go crazy beyond number situation. And that was the outcome of this project, that I did able to figure it out how to not to go for high performance computing, but for the PC-based regular simulations. Thank you.
Thank you very much. You had 3 seconds left. That's very fine. So this was number 3, 5, right? Yeah.
Yeah, 5.
Yeah. So now it's number 6, Josh Williams. Just 1 minute so that okay.
Can you hear me okay?
Yeah, we can hear you. Great. Okay, yeah, you're talking about inhalers. Please start now.
Thanks, Bernard. My name's Josh Williams from Heriot-Watt University in Scotland. So I'll be talking about my PhD over the last few years. So respiratory disease limits the lives of around 1 billion people and can places a pretty significant strain on healthcare systems. So these diseases are managed with inhalers, but changes with patient breathing and the shape of their airways means that they'll get a different effect from patient to patient. Next slide, please. So what we want to do is see how the drug from an inhaler deposits in individual patients. So to do this, we take patient medical images, in this case, CT scan. We extract the airways, and already we can see differences in size and shape, branching angle, which will influence the airflow and the drug particle deposition. Next slide, please. So we use these airway surfaces as a boundary for a snappy hex mesh, and then we can do simulation with LES turbulence model for the gas phase, two-way coupled to Lagrangian particle tracking. And we do this in OpenFOAM with the MP-PIC foam solver. And then this gives us some really nice analysis of how the individual drug particles deposit in different regions, so left lung or right lung, but also we can get local concentration like shown in this figure. And we can use this information hopefully in the future to aid doctors in making treatment decisions. Next slide, please.
That's the animation, right?
Yeah, the video.
Here we go.
Yes, so another benefit from these models, once we showed them to some patients, is that it could be a really great educational tool. So for example, particularly for child and young patients, if we show them videos, okay, if they breathe too fast, a lot of the drug will be stuck in the throat and the upper airways. And then if they breathe slower, we can show them a real visualization of the drug going deep into their own lungs, which would probably improve their technique and how much dose they receive. Next slide, please, Bernard.
Yeah.
Yes, so finally, I'd just like to end with this figure. I think it gives a good example of the need for these models. So we can see 2 different patients and 2 different breathing profiles, both with the same drug. And also I should mention that there was the same total deposition in all 4 models, but we can see across all cases the drug itself clusters in different hotspots, and in some it's more uniformly distributed, which would give a different therapeutic effect. So I think that shows the need for the model quite well. If anyone's interested in learning more about this, we have a medRxiv preprint with the DOI there, and also anyone can email me. I'm happy to answer any questions.
Thank you very much.
Thanks.
And the last official presentation. The last official presentation will be by Patrick Höhn from TU Clausthal. Please, Patrick.
Thank you for this opportunity today. Next slide, please. For the motivation, last year in the OpenFOAM workshop, there were discussions about how to be more friendly to beginners and also which other forms of discussion were there in the message boards, where I was also fairly active. Luckily, nowadays, we also have the Discord server, which is heavily used. But apart from that, I also started last year after the workshop another initiative. Every month, a couple of people are meeting up to discuss about OpenFOAM who don't have anyone else in their research group who use OpenFOAM. Maybe they are surrounded by ANSYS users, which does not give so much overlap. So there is this monthly meeting in order to also allow people to discuss maybe problems in OpenFOAM, what is good, maybe also other topics. It really depends also a bit on who is joining. And so far, this is what I'm keeping up, and I also would like to advertise it today. Next slide, please. So this meeting happens once a month since July last year. I always announce the date and the login details on CFD Online. And there I have, if you want to get the login details, either contact me or there you find them, but you need to be registered because it's as an attached image, just to avoid spam, that it spreads with spammers. And yeah, as I said, the discussions are going not only on OpenFOAM, sometimes also on open source software. It really depends on the audience, which has been quite fluctuating. Next slide, please. And our next meeting will be on the 23rd of July at 16 o'clock German time. I hope I meet people there, and also in between, one can contact me if one wants details. So far, as I said, the attendance has been quite fluctuating, but I'm looking forward for more of you to join me and discuss whichever topics you are then interested in. And yeah, I hope that it will stay alive and more people join me in, not just the 2 or 3 which have been regularly so far. With that, thank you for giving me the opportunity.
Thank you very much for presenting this interesting initiative to the others. Yeah, as a closer, I would like to do my own splash talk. It's going to be a bit shorter, I hope, and I haven't prepared any slides. This is in the spirit that during the live event splash talks, we usually give people the opportunity to also walk up to a blackboard and just tell about their problem, but if they can do so in 3 minutes. And I just wanted to tell you about one thing on the OpenFOAM wiki that I think is very nice. I still see people using their OpenFOAM shells without it. Because usually when I'm on an OpenFOAM shell and now I want to know, okay, I know I use an OpenFOAM version, but it looks like this, then the only way used to be for me to see which OpenFOAM version I was using without executing an utility would be to which interfoam, and then I'd see, okay, it's version 2012. And usually the first thing I now do when I get to a machine, then I modify my bash RC. I basically copy in this string, which basically is a bit of shell magic. And now every terminal I open tells me which OpenFOAM version I'm currently using. Of course, this is just of interest for people who are polyfoam like me, and not for people who are really monogamic with one OpenFOAM version. Okay, thank you very much. Thank you for listening to the others. Please contact them about details in their splash talks. And I hope to see a lot of you next year at the splash talks. I hope the organizers, whoever that may be, will let me do them again. Okay, thank you very much.